to the organizers for putting this very enriching and diverse workshop together. So I will talk about quantum dynamics, especially in conformal field theories, where we have some exact solutions, and the setup will also be out of equilibrium. So there will be some meaning of these waves rising up at some point as we go on. So this is work based with these collaborators and these two papers and some work which is about to come. Krishnendu was here until yesterday. So the main question and the setup that I will focus on will be the setup of the quantum quench, where I will make one parameter of the Hamiltonian dependent on time. So that is how I will drive the system. And so therefore the quantum evolution of the state will be quite complicated because the Hamiltonian keeps changing in time. And then this is the generic non-equilibrium scenario, and one can imagine tuning this coupling through the critical point, or as I will mostly analyze in this talk, will be switching between two values of the coupling suddenly. And the questions that I will be interested in will be to ask how do the observables behave as function of time? As we proceed in time, what happens to the observable? And then at late time, is there any simple description? Is there any steady state, universal steady state which appears? And as I was telling you, the setup will be where I will have a Hamiltonian for time t0, then I will have a different Hamiltonian for time t1, and this is, as most of you will be knowing, this is also called the Floquet setup. And what I will be asking, the question that I will be asking is, if I do this periodic change for n cycles, then where does my system, quantum system, end up? Okay, so the question is just that, and the scenario where we will ask this question is where we know the answer, okay, and where we can say something about the final late time steady state. This will be the outline. So the outline will be setting it up first in 1+1 dimensional conformal theories. Conformal theories, there are a few reasons for considering conformal theories. One is that it's very ubiquitous. One can think of it as building blocks of all quantum field theories, which can be obtained by deforming from the fixed points. And these are also very closely related to critical phenomena. And here actually there will be enough symmetry to answer this question when I choose my H0 and H1 suitable. So we will have some exact solution of the dynamics, and we will try to understand them geometrically using symmetry. And also some part of this story will generalize also to continuous driving, not just to the stepwise H0, H1, H0, H1. And there will be, I'll show you some also supporting lattice fermion numerics which can see these phases. And later part of the talk will be to discuss this setup also in higher dimensional conformal field, because the structure that we will use will continue to be there also in higher dimensional CFTs, and especially in 3+1 dimensional CFTs there will be a nice geometric understanding once again. And then I'll continue with some open questions. So if there are any questions, please feel free to interrupt and ask at any point. So I just informed you that I will consider very specific Hamiltonians for these two intervals. So H0 for me will be just the CFT Hamiltonian whose spectrum is the set of all critical exponents, and H1, and because it's a local theory, so I can always write it as an integral of a density, which is the stress tensor, and the deformation, which will be this H1 Hamiltonian is not the CFT Hamiltonian, but it will be a deformed Hamiltonian, which will be deformed in this way, that instead of integrating the local density, I will put in a factor of sin square x by. So this is called the sin square deformation. And what it is effectively doing is, if you imagine there are uniform bond strengths, it's increasing the strength in the middle of the system. So usually I will consider the theory on a circle for 1+1. The space is a circle, so if you fix boundary at some point, you call it 0. So what I am doing is I am picking up the center, turning off and if it's open boundary, then I am kind of ignoring the edge effects or the boundary effects. But this turns out to be very special because it turns out that this function allows for some analytical analysis that will finally let us relate this Hamiltonian also to a CFT Hamiltonian, and that is what will help us solve the system exactly. And these are the set of people who have been working with this deformation or some generalizations of this deformation. There are many more which I may have missed. And the idea is simple. So because it's a CFT, we can always go to, we are allowed to do conformal transformations. And it turns out that there is a conformal transformation which will take this Hamiltonian also to another CFT Hamiltonian, as I was mentioning. And it's actually, for this class of deformations, it's easy to find deformation. So the entire dynamics will be contained in this conformal transformation, so which will allow us to tell what happens at late times and how correlators behave. And this will finally, this will give us, from the property of these transformations, we will actually be able to figure out geometrically why these phases arise in steady state. So more generally, the deformation is some function multiplying the stress tensor and you integrate. And the goal is to relate it to a CFT Hamiltonian to find a frame such that this takes this form, z times the stress tensor. And this is possible to solve for this z tilde because we know how the stress tensor transforms under conformal transformation, because it's an operator in a, originally you start with a CFT. So you know how this transforms, and because you know how it transforms, and this this is just, there will be a Jacobian factor, so we can solve a differential equation which can take us from this deformation to, from this Hamiltonian H1 to a Hamiltonian L0 in some conformal frame. So there is a way to find out the conformal transformation. And it turns out that in this case it is just a Mobius transformation, which looks like this. So z goes to z tilde, which is az plus b, cz plus d. This is SL2R, if these are real numbers, with determinant 1, AD minus BC will be 1, and that will turn out to be the scenario for all Hermitian drives. And once I know the transformation, then I can figure out by conformal symmetry, because this is a conformal transformation, I can figure out what are the correlators at any time. So if I have to do it, if I have to repeat this process, if I have to go from H0 to H1 and again go from H0 to H1 and so on, I just repeat this n number of times if I have to do it n times. And there is a very nice way this map can be written down if I have to repeat this n number of times. And once I know what the final coordinate transformation is for any scaling operator with dimension h, I can figure out how it behaves as a function of space and time, just using conformal mapping. And it turns out that you can get different kinds of behaviors. So if you look at the energy density itself, how it changes, one gets three phases, three distinct phases. In one of the phase, so remember one is driving the system, H0, H1, H0, H1, but there is a phase where the system, where the energy density simply oscillates, doesn't blow up, keeps oscillating. That's why it's called non-heating phase. There is a phase where energy accumulates in two positions. If I take the circle, the space as a circle, it concentrates on pi by 2 and 3 pi by 2. Okay, and these colors indicate what happens at late times. So red is very late time and green is early time. So it keeps exponentially localizing. And there is a critical phase where there is a power law accumulation of energy, power law behavior of energy with time, and that is a boundary between these two phases. And these are exact solutions, and there is a very nice mathematical way to understand why these are the only three cases which arise. And I'll just skip this. So even in case of continuous driving, where I drive with some frequency, I can see in my phase space, so delta f is a constant DC piece and omega is a frequency. In this phase space, I can also see all these phases. There is some fractal area near omega equals to 0, near the low frequency. And there's an example So one can also see this with lattice fermions. One can also get these two phases by just tuning these omegas and the constants J0 and J1, delta F and omega. Yes, yeah, that's what I will say now. So this is a way of writing the Mobius transformations, that one can write it in terms of the fixed points. So if T is a Mobius transformation, so what this transformation is doing is that, so there are two fixed points of the Mobius transformation, because it's, if you solve for the fixed point, you get a quadratic equation. So what this right hand side map is doing is sending 1 point to 0, 1 to infinity, and then this is this eta, which can be complex. It's also a function only of the fixed points, is causing a dilatation and a rotation, and then this is a map back. So any Mobius map T can be written in this way, and if you repeat this, then you just keep getting, if you do it twice, you just increase the power of this eta. And if you look at what is the conformal factor, it will be this eta power the time. That will be the conformal factor. So whether the energy is going to get localized, increase or oscillate, depends whether this eta is a pure phase or is it a real number, or is it a case where the two roots collide. And this is again all in Euclidean, but we are doing real-time dynamics, so later we are always doing analytic continuation. That's one subtlety, but these are the three possibilities. If it's a pure phase, then it just goes around the fixed points. If it's, and that corresponds to that oscillatory phase. If it's real, then it goes from one fixed point to the other, that's the exponential phase, and then there is a boundary, which is parabolic. So these are the three classifications, and yeah, there is some subtlety about Lorentzian, I'll not go into. So there will be two roots always, one will be greater than one will be less than one. So the less than one is where the cooling occurs. So and so it also depends on the value of x. So only, so it breaks the spatial symmetry also. Okay, so I'll switch over to higher dimensions. So actually what gave rise to this Mobius was a global subgroup of the infinite dimensional conformal group in 2D, which is Virasoro. So we used only the SL2R part, which under analytic continuation became SL2C. But this global subgroup is also present in higher dimensions. So in higher dimensions, if I take the dilatation, the momentum generator, and I choose the spatial conformal transformations, then I can again form my SL2R algebra. Actually, there's also other way of constructing these groups, and we have done it also including rotation. So, but once you have this subgroup, then one can again play this game, same game. And it turns out that now the fact that we were using this Mobius transformation, that in 3+1 dimensions there is a nice generalization in terms of quaternions. So you get all the space-time coordinates coupled in terms of a quaternion, right? Represent it as a quaternion, and then you can show that in 3+1 dimensions, any conformal transformation can be written as a quaternionic Mobius transformation. And because it's of this form, many of the technologies that we used for 2 dimensions, we can just import. And this turns out to be very useful. And the group of these quaternions is called SL2H in 4 dimensions. And there is also a conjugacy class classification of SL2H. So one may expect, just as the conjugacy classes of SL2R gave us all the different phases, the conjugacy classes of SL2H may give us the phases for 3+1. And just to show that you again have all these characteristic phases, so if I start with a finite energy density state and I deform in the 0 direction for time t/4, then in the 3 direction for time t/4, and I go back along some other direction, one direction, so that the net time is t, I go back, so this is U dagger. So this will give me some, and I take overlap with the original state, this will give me some sort of a fidelity. And what I can see is, depending on my Hamiltonian deformation parameter, which is beta in this case, I can either have a full recovery or I can have zero recovery of the state. Okay, so zero recovery corresponds to this heating phase, full recovery corresponds to this non-heating phase. And there are other markers also, so one can also see oscillations in energy density. Now I look at oscillation about any angle, I take projection, I find oscillations, and I find localizations of energies. So this black line is later time, this green is some early time. So as time progresses, at late times in the heating phase, I have localizations of energy. And again, there is some reach phase diagram, and one can again understand this again in terms of these fixed point structures. So now, this again, the elliptic class was going around these fixed points P and Q. So now this is not 3 plus 1 but 2 plus 1. So one of the coordinates I have set to 0. So now instead of fixed point, it's a fixed surface. So which is this circle, and what the trajectory does is goes around this circle. So the circle is this intersection of this cylinder with this plane, and the trajectory are these red dots. So they go around. This is a Euclidean picture, and this is what happens in the elliptic phase. This is the non-heating phase. And again, so there is this math paper by Parker and Short, John Parker, Ian Short, where they classify the conjugacy classes of SL2H. There's an algorithm. They tell you what are the things to be computed from these quaternions and what are the things to look at. But once again, there are only 3 phases in all cases. It's either heating, non-heating, or something in between, the boundary. And even though our entries are not real, our entries are complex because we have real time, it turns out for the situations that we checked that the dynamics follows this classification. So for example, if I do a 2-directional drive, so x, so for time t1 I drive in the x direction, and for time between t1 and t1 plus t2 I drive in the y direction, 2 different deformations. Then there can be, depending on beta 1, beta 2, t1 and t2, I can land up in any phase, and depending on these parameters I can be in any conjugacy class of SL2H, and this is the class. So this 3D region is the class of points in the parameter space where I have non-heating phase, and we find exactly here the eigenvalues of the evolution matrix to be unit moduli, so that they are just oscillating. Okay, so we get the same shape by looking at pure phase nature of all the and in hard, and so now, so this is something is inherently higher dimensional. We cannot do this in 1 plus 1. So you do the floquet, 3-step floquet. So you drive x for time t1, then y, then t, then z in z direction for the next cycle, and then you keep repeating this, and then you find that the region of this non-heating phase goes down. It's almost, it's very difficult to locate them, even from the Parker-Short classification. But one can again check this classification. So you can, so these areas are where one expects non-heating phases in the beta and t phase space, and if one zooms in into these points, one finds the eigenvalues again lie on a unit circle. The other eigenvalues, they are just scattered. Those are the those are not elliptic. Those are the loxodromic. So I'll conclude. So what I told you, that exact real-time conformal drive because both the Hamiltonians can be mapped to some CFT Hamiltonian, can be classified using conjugacy classes of the corresponding Euclidean subgroup, which is SL2R in one case, SL2H in the other case. And this is slightly richer because it allows for also multi-directional drives. However, there are always 3 classes. The flows, there's a nice holographic story which I did not mention, and there are things that match from that side. There is a curious fact that the operator, the real-time evolution operator with the heating Hamiltonian maps onto a thermal density matrix for the non-heating Hamiltonian. Okay, and it's weird, but it actually turns out this is true, and all the subtlety lies with the spectrum of this heating Hamiltonian. And some open directions before this is the last slide. So this H1, even though it appears to be a concocted Hamiltonian which allows for relating to another CFT, this actually appears very naturally as a modular Hamiltonian, which is log of reduced density matrix if you are calculating an entanglement entropy. And so this dynamics that we are looking in real time also has some meaning if I want to evolve with the modular Hamiltonian. And there is a generalization of this Mobius to arbitrary dimensions. Instead of SL2H now, there will be a Clifford group instead of quaternions. So this has been recently worked out by Orithro, Pal and Kaushik Rai. And of course, a big open question is so conformal symmetry played a very important role. Big open question is to deform from conformal symmetry, and techniques like, so one has to develop some non-perturbative techniques, and maybe using TCSA, truncated conformal space approach, one can see how the dynamics is changing. Thanks.
Thank you. Questions? So you have this Hamiltonian H0, H1, H0, H1, right? And your times were fixed, right? T0, T1, these are fixed times,
fixed
right?
Time, yes.
So then this system goes to a time periodic steady state, no? Instead of a steady state, I guess, right?
Yeah. So there are three possible steady states. In one, there is always oscillation with respect to the. So we are looking at stroboscopic time. We are not looking.
You are looking at the stroboscopic time.
Only stroboscopic.
Okay.
So we are not looking micro motion.
Yeah. Okay. But if you make those times random, so then you have a really steady state, right?
Yeah. So this is something Ashwin, Vishwanath, and others looked at.
Okay.
And there, I think they only end up with heating phase, if I remember correctly.
Yeah, you will have heating in this case because
Yeah, there is some Furstenberg's theorem which they used to show that behavior will always be Lyapunov. If you multiply random matrices together, then the maximum eigenvalue will be positive.
Okay.
Something.
No, I was just saying that even the time, this T0, T1, these are just random times.
Yeah, if these are random times, then the evolution matrix entries will also be random.
Random, yes.
So this correspondence between the heating evolution and the something that looked like a thermal density matrix, that's a little curious because the left-hand side seems to be a unitary operator and the right-hand side seems to be a non-unitary operator. How does it work out?
So this Hamiltonian, so this is both the Hamiltonians are Hermitian Hamiltonians.
Okay.
But the reason, so this heating, so what we think is the case is this heating Hamiltonian has a unbounded spectrum, continuous and non-degenerate. So for every energy E, there is an energy minus E. Okay. If I, for example, compute trace on both sides, this right-hand side will give me a real quantity, but the left-hand side will also give me a real quantity because it's non-degenerate, and for every energy E, I have an energy minus. So the exponents combine to give you cosine.
So you are saying when you take traces of both sides, then it's equal, or as operators themselves are equal?
They are themselves equal, but I am just saying that because these are Hermitian operators, you expect the trace to be a real number.
That's about traces, but I'm saying the eigenvalues of the left-hand side are phases, no? And the right-hand sides are some e to the power minus 2t times some real number. So how would this?
So this I can maybe I can show you in more detail.
Okay. Thanks.
So just one comment is that the relation between these two Hamiltonian is not a unitary operator. They are related by a non-unitary operator, but it's a similarity transform. Yeah, Hamiltonians are self-adjoint.
Okay, so if there's no more question, let's thank the speaker.
Long live India and France friendship.